Optimization sits at the core of modern deep learning systems, yet it is one of the most misunderstood areas among early and mid-career practitioners. In real-world AI teams, performance issues are far more often caused by poor optimization choices than by model architecture. Many professionals treat optimizers as interchangeable configuration options rather than as mechanisms that directly shape learning dynamics. This leads to unstable training, poor generalization, and wasted compute budgets. From a career perspective, misunderstanding optimization limits one's ability to debug training failures and meaningfully contribute to system design discussions. Senior engineers and researchers are expected to reason about convergence behavior, stability, and scalability. This lesson focuses on building that level of understanding so optimization decisions become deliberate and defensible rather than trial and error. These objectives reflect what is expected from professionals working on production scale or research grade models. In industry settings, optimization decisions influence training cost, iteration speed, and reliability. A common misconception is that tuning optimizers is an implementation detail rather than a core modeling decision. This mindset often leads to fragile systems and slow progress. Practically, engineers who understand optimization theory can anticipate failure modes and design more stable training pipelines. This capability directly impacts career growth as it distinguishes individuals who execute instructions from those who can independently diagnose and improve learning systems. Loss landscapes in deep learning are high-dimensional and fundamentally non-convex. In real AI teams, this reality explains why training behavior often appears unstable or unpredictable. Many practitioners mistakenly reason about optimization using low-dimensional intuition, expecting clean minima and smooth convergence. This misunderstanding leads to frustration when models behave inconsistently across runs. Practically, recognizing the prevalence of saddle points and flat regions helps engineers interpret noisy gradients and slow progress. From a career standpoint, this conceptual clarity enables more confident debugging and more credible communication with research and platform teams. Stochastic gradient descent remains the foundation of most deep learning optimization strategies. In production environments, its simplicity and robustness make it a default choice. However, many professionals underestimate the role of stochastic noise in escaping poor regions of the loss landscape. Treating noise purely as a nuisance rather than a feature leads to overly aggressive smoothing and slower learning. Practically, understanding SGD variance allows engineers to control convergence behavior more precisely. This competence reduces training failures and builds trust in one's ability to manage large-scale learning systems. Momentum-based methods accelerate training by accumulating gradient information over time. In real-world AI teams, these methods are widely used to stabilize training on noisy objectives. A common mistake is enabling momentum without understanding its interaction with learning rate and batch size. This often results in divergence or erratic loss curves. Practically, professionals who understand acceleration mechanisms can tune systems more efficiently and avoid wasted compute. This skill becomes increasingly important at scale, where small inefficiencies translate into significant cost and delivery delays. Adaptive optimizers such as ADAM and RMSprop adjust learning rates based on historical gradients. In industry, they are often chosen for convenience and fast early progress. Many practitioners assume faster convergence automatically implies better final performance. This misconception can lead to models that train quickly but generalize poorly. Practically, understanding when adaptive methods help or hurt allows teams to choose optimizers aligned with long-term objectives. From a career perspective, this judgment differentiates senior practitioners from those who rely on defaults without critical evaluation. Second-order methods incorporate curvature information to guide optimization. In theory, they offer faster convergence near optimal points. In practice, their computational and memory costs limit widespread adoption in large models. Many professionals overestimate their practicality after encountering them in theory. This mismatch can lead to unrealistic system designs. Practically, understanding why second-order methods are rarely used at scale helps practitioners make grounded architectural decisions. This realism is valued in senior roles where feasibility matters as much as mathematical elegance. Natural gradient methods adjust updates based on the underlying geometry of parameter space. In advanced research teams, this perspective is valuable for understanding optimization stability. However, many practitioners mistake conceptual appeal for practical readiness. Approximating Fisher information at scale remains challenging. Practically, professionals should view natural gradients as a guiding framework rather than a drop in solution. This balanced understanding prevents over engineering and supports sound decision making in complex projects. Batch normalization is often introduced as a training stabilization technique, but it also acts as a form of regularization. In production systems, it significantly alters learning dynamics. Many professionals treat it as a purely architectural component and overlook its optimization effects. This can lead to confusion when removing or replacing it changes convergence behavior. Practically, understanding batch normalization's role helps engineers reason about training stability and generalization. This insight reduces trial and error and strengthens system level intuition. Learning rate schedules control how aggressively models learn over time. In real AI teams, scheduling often has more impact than optimizer choice. A common mistake is using fixed learning rates throughout training, leading to suboptimal convergence. Practically, professionals who understand scheduling can extract better performance without changing model architecture. This capability is especially valuable under tight compute budgets and directly influences delivery timelines and perceived technical competence. Warm-up strategies and curriculum learning address instability during early training phases. In large-scale systems, abrupt optimization often leads to divergence. Many practitioners ignore warm-up, assuming models should handle full learning rates immediately. This oversight causes avoidable failures. Practically, applying warm-up reflects maturity in training design. Professionals who use these techniques effectively are trusted with scaling models and managing complex training pipelines. In deep networks, saddle points are far more common than poor local minima. In production environments, stagnation often occurs when optimization dynamics fail to escape these regions. Many professionals misdiagnose this as insufficient model capacity. Practically, understanding the role of noise and clipping allows teams to address stagnation systematically. This diagnostic ability improves reliability and reduces reactive redesign cycles, supporting sustainable career progression. Generalization theory attempts to explain why overparameterized models perform well. In industry, empirical behavior often outpaces theoretical guarantees. Many practitioners either ignore theory entirely or overinterpret it. Both extremes are problematic. Practically, understanding concepts like flatness and double descent provides intuition without false certainty. This balanced perspective helps professionals make informed decisions and communicate uncertainty responsibly, which is critical in senior technical roles. Large-scale models introduce optimization challenges that do not appear in smaller systems. In modern AI organizations, efficiency and stability at scale are primary concerns. Many professionals underestimate the complexity of distributed optimization. This leads to fragile pipelines and delayed delivery. Practically, understanding large-scale optimization techniques enables engineers to contribute meaningfully to flagship systems. This experience is a strong hiring and promotion signal in advanced AI teams. The next lesson shifts focus from optimizing a single task to optimizing across tasks and data regimes. Few-shot and meta-learning challenge traditional assumptions about training and convergence. In professional settings, these approaches are increasingly relevant as data efficiency becomes a priority. Many practitioners underestimate how deeply optimization concepts carry over into these paradigms. Practically, building on today's foundation prepares you to engage with these advanced topics confidently and positions you for roles at the forefront of applied and research driven AI.